So what we've gone and done so far is actually put in all the diodes on the board and also the resistors. So I've got a taped piece of printed circuit board which we use for measuring. Right, we can come in and we can get a cross measurement, and we can either mark that on this board or just take a general reference, and then we can bend the component to the right shape to fit in the hole. Once we've done that, if it's a requirement to keep the components off the board, we just simply put the printed circuit board underneath the component, and then we just lay it over and then do the soldering on the opposite side. Now the interesting part with this board is that it's double-sided, so we've actually had to go through and solder on this side first and then come back and go through all this side as well on both sides of the component, just to make sure that we've got good contact. Now another part of the board components and the first parts that we actually put onto the board were the surface mount. We had 4 of these capacitors, so we had 3 here and there's 1 over here, and we had this resistor. We've progressed with the board. We've got all the components on that need to go on, and also the IC beds. Now basically what we did here, we just basically started off at the lowest profile, which is your surface mount, and then we just worked our way up, in size, so that we could work on the board easily. So this is the top side of the board. The underside of the board, as you can see, is also got a range of components on it. You've got 2 transformers, your large caps, and some ICs that fit to the actual bottom of the board. The last thing that we did is that we just went through with isopropyl alcohol, and we just cleaned off both sides of the board and got rid of all the flux. So we've got the heat sink. So the main board actually fits onto this heat sink. You got a thermistor here. Now originally this was going to be soldered, or the leads were going to be put from under the board and through. We found that to be a bit of a restriction and quite difficult to do, so I've extended the leads out and we'll solder it from the top down. And we'll also put on the side supports on both sides, or both ends of the heat sink. And that was an interesting saga because we had to get all the measurements and there was nothing given to us as to what the distances in that were. So with the box itself, I think last time we had the output put on, and we've actually got the wires attached to that now. The fan has been put on, and I think we showed you that last time, and we've also put in for the cable gland, which is the input cable, and this small screw here is just the retainer for the cable coming through, so it's out of the way. So to fit the heatsink in and the supporting brackets was an interesting saga. There's not enough room in here to get an actual ruler in, and there was no dimensions given us for the spacing of the securing point. So it was an interesting saga trying to find our centers, and you could do that roughly by eye, but what I ended up doing was just getting a piece of board that fitted across that way, and I could work out where the outside dimensions were, work out what this was, and then do your normal subtraction and find your center points. So what we're going to do now is mount the board onto the heatsink, and as you can see here we've got the machine screws for that and the spacers. The spacers fit from the heatsink to underneath the board obviously, so what we'll do is put them on first just loosely. We've got heatsink compound, and that goes on these 2 ICs here. You don't need a super amount on, but nice and evenly spread. So we've got the spacers on. Now we need those loose just a little bit because we've got to get these screws here that actually hold the ICs to the heatsink. So we're going to get the screws in reasonably straight. We'll just use the magnet to, that one's in, so that's fine. So what we'll do now is go around and tighten the board down. But and we're basically doing this now because we needed the alignment for the screws for the two ICs. Alright, so one of the components that we had to put on last, due to the screw hole that's underneath it, is this thermistor here. So we just soldered that in. So the next one we're going to solder in is these two wires here, and they go to what's called Con 7 or Connection 7, and that's another thermistor that's actually attached to the heatsink. So we're just going to be lining it up with the holes that we've drilled and the mounting points. So our next connection that we need to solder in is for the fan. Here they've provided some heat shrink that goes on the fan as a bit of protection for the wires, and they go into these 2 points here. So as you can see here, we've got our fan wires soldered in. Now there is a positive and negative to make sure that the fan runs the right way. So that's marked on the board, and you just solder accordingly. So what we're going to do now is just wire in the right connections for your power in. So it goes to this right block here, and also your power out, which goes to this block here. We've got all the wire connections put on and the wires put into their various blocks. So as I said before, this is for your input side. So this is coming from your single phase supply. This is your output side, which can be either single phase or three phase, depending on how you wire it up. At the moment it's set up for single phase, so you can just put your motor across there for a single phase motor. But there's only particular types that this will support. But it's more designed for three phase operation, so you can go from single phase to three phase, and you just add a white wire here which would go to that center one, and your motor would have to be in a delta configuration. We just used a couple of cable ties just to tidy things up a bit. The other one that we had to add on was a ferrite bead which goes onto the output side of the connections. We put that on. Next thing we're going to do is just put our ICs in. The first one we're putting in is an octet coupler. This is only a 6-pin IC. We've got two other IC couplers to go in. And just press them down gently. Make sure your pins are lined up before you push it down so you don't damage anything. The LM319. So this is our next IC to go in, and again make sure it's orientated the right way. Just adjusting the pin spacings a bit so it goes in. You can tell with your chip you've got a notch in one end of your bed, as long as you've got your bed orientated properly on your circuit board. And pushed in, it should all be bedded in there nicely. And this large one here is a pick. They're using a pick 33FJ64MC, and that's all been programmed. Your notch up here, your notch on that side of the bed. They're all in both sides, and it's orientated the right way. And then you can push that one down. So you can see we've got a high-speed comparator in, that's the LM319. We've got two 8-pin opto-couplers and one 6-pin opto-couplers, and this one goes in backwards to the other two. You've got to be aware of that on your board, and this is your PIC IC. We'll just put our cover on, or a protection cover for our fuse. We've got power applied to the unit, and what basically happens here, you put this connection in here. This is for your run winding. We've got the two variable resistors at about midpoint, and all our switches are to off. Now what happens when you first put power on, the green LED here flashes for a short time and then comes on solid, which basically indicates that the PIC is operating properly. You've got the neon glowing, that just lets you know that there's power on the circuit. There are some very large capacitors on the back of this board which hold very high potential, so you've got to be very aware of that. And the other thing is that when you're first testing a circuit like this, you should basically do it in isolation, which is what we did. Took it outside, we put it on an extension cord, connected it up, and then applied power to see what happens. The issue is that those large electrolytics can explode, and they're basically like a small grenade when they go off. So double check everything, make sure it's all around the right way, and soldered up properly and in the right place. And always check in isolation first before you put it on a test bench like this. We'll put it on the bench, and we've now got power applied. And what basically happens in that situation, as I said earlier, the green LED flashes for a short time, then comes on solid. That basically indicates that your PIC is working properly. The neon comes on to let you know that there's voltage on the circuit, and the voltage potential across the capacitors, if you watch on the multimeter, is a bit over 300 volts. So there's quite some serious potential there that could cause harm if you're not careful. This is basically designed for induction motors up to 1.5 kilowatts, and it's suitable for either shaded pole motors or your permanent split capacitor motors. Now anything else that's listed here, such as your capacitive start, capacitive start and run, and your centrifugal start switch type motors, it's not suitable for. So what we have here is the right connection for your various types of motors that you can run, and as you can see here, they've got a or what they're saying, a pool pump stand alone type mode. So you can have your motor, which is a single phase motor, as long as it's the right type, and you just have your link in, which is what we've got in, just to make sure it runs. You can either have a single phase external mode, basically the same setup in this area, but you have changed a few things here. So now you've got a speed control, and you've got a start stop run, which you can do. Or you can have a 3-phase connection, as you see here, you've got your red, white and blue for all your individual phases, and you can have your speed control, and in this case you can actually use the run and reverse modes as well. Now this terminal block here is what all this is set up on. So you can see your potentiometer for your speed control, you can see your run, reverse and emergency stop situations here. You've got 2 earth points, and you also got an output pin as well. So we'll put the cover on. So the important part about this project, for the reasons why we did it, is to control basically a 3-phase motor on a small lathe, and to give us external controls for speed